In this lecture, we are going to talk about the gradient and the Hessian for the case that your variables are either vectors or a matrix. So let's get started with the gradient. Suppose that f is a function that its inputs are n by n matrices and its outputs are a scalar. So it's a function that takes matrix A, which is n by n, and returns a real value. All right, now we want to see what's the gradient of f. Gradient of f with respect to A, which is a matrix of variables. So before doing that, something that I would like to note is the size of the gradient is the same size of the variable. So for example, in this case, your gradient of f of A with respect to A is an n by n matrix, which is the same size as A. What are the elements of this partial derivative of f of A with respect to the first element of A? Partial derivative of f of A with respect to second element, and so on. This way, partial derivative of f of A with respect to A m1, partial derivative of f of A with respect to A mn. Let me write down A here just to have an idea of how it looks like. A11, A12, A1n, AM1, AM. So A is also n by n. So this is the gradient of function f with respect to matrix A. A special case of this is the case where A is a vector. So if A is a vector, for example, A is n by 1, and we call it x, so it's vector of x n by 1. In that case, gradient of f of x with respect to x, again, it's going to be the same size as the variables. What is the variable? Xn by 1 is x1, x2, x sub n, which is n by 1, right? So partial derivative of f of x with respect to x1, with respect to x2, and with respect to xn. This is the case that we usually see in the optimization problems that we deal with in this course. So we have a vector as our variable. There are two very important notes. One, gradient of a function is only defined if the function is real valued. And also this is equivalent to saying that gradient of a function is only defined if it returns a scalar value. So it should return a scalar real value so that the gradient exists. So there are also two properties of a gradient. Properties of gradient. One. So the first property is gradient of f of x plus g of x with respect to x is equal to gradient of f of x with respect to x plus gradient of g of x with respect to x. The second property, for a real value like t, gradient of t multiplied by f of x with respect to x is equal to t multiplied by gradient of f of x with respect to x. All right, now that we reviewed the definition of gradient for the scenarios where your input variables are either matrix or vector, we are going to talk about the Hessian. The Hessian. Suppose that function f from Rn to R. So again, output is a real value and a scalar is a function that takes a vector which is n by 1 and returns a real number. Then the Hessian matrix with respect to x, which is denoted by or simply sometimes we show Hessian matrix by H or Pascal H. The calligraphy is the n by n matrix of partial derivatives. How do we define that? So the Hessian matrix is equal to so our input was x, which is x1 to xn, so it's n by 1. Hessian matrix is n by n. So second order derivative of f of x with respect to x1, second order with respect to x1, x2 of x, x1, xn, x2, x1, then second order xn, x1, and finally second order derivative of f of x with respect to xn. All right, so where do we use Hessian matrix? For convexity. So if you remember, we talked about positive definite, negative definite, and before we defined convexity. So that's where we have to calculate, we have to find the Hessian matrix. And if I want to write the Hessian matrix of the function f in the closed form, So element ij of Hessian matrix, element ij of Hessian matrix is equal to second order derivative of f of x with respect to xi, xj. And also another thing to note, Hessian matrix is always symmetric. What's the reason for that? Just a side note, because second order derivative of f of x with respect to xi, xj is equal to second order derivative of f of x with respect to xj, xi. So the Hessian matrix is always symmetric. So in this lecture, we talked about the gradient and the Hessian matrix. So if we want to find the gradient of f, which is a function of matrix A, with respect to A, let's say A is m by n, and f is from m by n space to real values. Then element ij of the gradient for f is partial derivative of f of A with respect to element ij of A. So we had the same definition for the Hessian matrix, where Hessian matrix, let's say we have f from n by 1 to real values. So element ij of the Hessian matrix is defined as second order derivative of f of x with respect to xi, xj.